Okay, we're on lesson 4 now. So our first 3 lessons were all about exploring a bunch of different rules, and we have that whole formula sheet. A bunch of those are kind of from the past, like the supplementary and complementary angles. And you learned about the Z rule, F rule, C rule. And in the last one, we were talking about, what did we actually get into in that one? Oh, the external angle rule. We said that an external angle is equal to the sum of the 2 angles inside the triangle that don't touch it. And we kind of proved that as well. So you do have to have these memorized, and you do have to be able to justify them. So this is a challenging unit. You are going to have to practice quite a bit and memorize those things. And keeping with that tradition, there's kind of 2 new rules in this section about larger polygons and angles, and then we're going to get into congruent triangles eventually, and there's 2 lessons on congruent triangles. So make sure you are practicing enough. Okay, so let's learn the new rule. This one should be fairly intuitive once you figure it out. Learning outcome, we're going to determine how property angles and polygons, and we're going to use these to solve some problems. A pentagon has 3 right angles and 4 sides of equal length. So this side, this side, this side, and this side are all equal length. It says only 4 sides. I guess this one's longer. Yeah, in order to make that true. What's the sum of the measures of the angles of the pentagon? You can use a protractor added up, but we should be able to figure this out on our own anyway. Basically, this one is 90, right? This one's 90. This one is kind of 90. This one is 90 if you want to think of it like that. This one up here is 90. Since this one is, these 2 lines are the equal distance, these 2 in here also both should be 45. So together they make 90. So if we add up all of these, basically they have one method for doing it. They basically said all the ones inside the square add to 360 degrees. All the ones in the triangle add to 180 degrees. And since these 2 objects are right beside each other, since they're sharing an inside, the sum of all the angles for all of them is actually just the adding of both these 2 things together. We can see that because all these ones stay the same, and these 2 angles actually do add together to make that angle there. They do get bigger. Same thing over there. So it is actually the sum of both of them. So the answer is 540 degrees for this entire thing. How is the number of sides in a polygon related to the sum of the interior angles? So we're going to investigate this, and we're going to find out the answer to that. With a partner, draw the polygons listed in the table below. Create triangles to help you determine the sums of the interior angles. I'm going to do a couple like that. Obviously, if we have a triangle, any old triangle, it's equal to 180. We know that as a rule, right? Any quadrilateral, so we say that's a quadrilateral. And what we can do is we can actually turn it into 2 triangles that don't overlap. And if we turn it into 2 triangles that don't overlap, then it's 180 plus 180. All the things inside a quadrilateral need to be 360 degrees. 5-sided figure, we already did. It equals 540. And it says there's 3 triangles. So basically there's 1 triangle up here, and they actually draw the dots this way as well. So there's 1, 2, 3 triangles not overlapping. That's the important thing. So when you're doing triangles, you always kind of choose 1 point to do them all from. And I'll show you with 6. So let's try this with 6. 1, 2, 3, 4, 5, 6. So there's a 6-sided shape. Now we need to make a whole bunch of triangles. So we need to pick a corner to start with. Why don't I use some colors here? Let's pick this corner right here. From that corner, we can start drawing a bunch of different triangles. So the first triangle would be straight across here. And then you pretty much go to every vertex from there on to make triangles. So if I go down to that one, I've made a triangle. If I go down to that one, I've made a triangle. And you can't choose this one. because there's already a line connecting it, same as you couldn't use the first. So basically it goes to every vertex that it wasn't originally touching. So how many triangles? 1, 2, 3. This has 4 triangles in it. So a 6-sided figure contains 4 different triangles. All those triangles add together, so it's 180 times 4 is, I'm not sure what that is, 720 degrees. Now, once we've had this much information, we can probably just see the patterns. So how many triangles will be in a 7-sided figure? There should be 5. In an 8-sided figure, there should be 6. What is 5 180s? 900 degrees. And what is 6 180s? 1080. Okay, so based on how many sides the figure is, and this does not matter how it's drawn, this is not the regular one. A regular shape is one where all the lengths are an equal size, like the square or equilateral triangle. So this doesn't have to be regular, it's literally every single octagon. As long as it's an enclosed polygon with 8 sides, all the angles in it will add to 1080 degrees. That's always going to be the case. So given the information you discovered in the table below, can you make a conjecture about the sum of the measures of the interior angles of a polygon and the number of sides of the polygon? So this formula, we always start with n. So we say let n be the number of sides of the polygon. And they usually do capital S, I believe. Let me just look. This same website doesn't say, but I'm pretty sure you use capital S. Let S be the sum of the interior angles. We've talked about interior versus exterior angles, so we know the difference. Interior is inside the polygon, exterior is if you extend a line outside of the polygon. So how are we going to actually do this? So we want to relate this number to this number. And there's a reason we built this column in the middle. It's because this column in the middle is really important to get to this last number, right? It was always this number times 180 gets you the final number. So the only thing we're missing is how do we go from here to here? And it's always 2 less, right? So that's basically what we do. We say the sum is equal to, you take your number of sides, and you take away 2. And that makes your number of triangles. So that is your number of triangles. If you want to try and memorize this formula, and you're going to have to, that's kind of what we mean by that. So an 8-sided figure, you take away 2, you get 6 triangles. And then all you have to do is times that by 180. And that's how we can find every single one. So it's not too complicated a formula. Hopefully we can memorize that. And let's see how it works. Okay, use your conjecture to predict the sum of the measure of the interior angles of a dodecagon. Dodecagon? I'm not really sure how to say that perfectly, but a 12-sided polygon. So we're going to say n equals 12 different sides. And we want to know what the sum of the interior angles is. So we say sum is equal to n minus 2 times 180. We sub in n equals 12 is equal to 12 minus 2 times 180. Basically means it's 10 triangles and 180 degrees a triangle. So the sum should be 1800. Just add a 0 when you're multiplying by 10. Very easy. Can you verify your prediction using triangles? So we need to make a 12-sided figure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yuck. I don't know if this is going to work right. We probably needed a better figure. Let me try again. Because we don't want any of these. That's no good. We want it all to be stretched outwards. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So pick a name. Pick a vertex. Let's use this one. And let's draw some triangles. Boom. Boom. I would say boom every time. If you're actually drawing this with straight lines, they should all be perfect triangles, actually. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 triangles. So 10 times 180 is 1800 degrees. So it does indeed work. Good. It's not easy to draw a huge picture like that. Try your best, or just hopefully you followed along. Now we're going to go on to the counterpart. There's actually two theories. There's two formulas that we need in this unit. The other one is it's actually much easier. Let's try and see how it works. So given the angles below, what do you notice about the sum of the measure of each exterior angle? So whatever A is, W should be 180 minus A, right? Same, whatever D is, Z should be 180 minus D. So as the internal one gets bigger, the external one is going to get smaller, right? Because it's going to have less room to play with. We could make up some numbers here, or you could actually measure it. Which one looks the smallest? I'm going to say C. Let's say C is like 60 degrees. That means over here is 180 minus 60. This would be like 120 degrees, right? So if it's small, this becomes big. D is the biggest one. That looks like maybe 130 degrees. That means Z must be only 50 degrees. So as the one on the inside grows, the one on the outside must shrink. So now let's think about that for a second. If we go back to our table, we saw that the sum of the angles on the inside is growing and growing and growing. That means all the individual angles must be growing and growing and growing, which means the external ones are constantly shrinking. So what do you notice about the sum of the measure of each exterior angle and its adjacent interior angle? So as the interior angle grows, the exterior angle shrinks. As the one on the inside gets bigger, the one on the outside must get smaller. So this is actually going to get to the rule. We're going to see the rule on the next page. But the sum of exterior angles is always equal to exactly 360 degrees. It's actually a really funny property that way. It doesn't matter how big your polygon is. So take this guy, for instance. There's a lot of exterior angles. You can make one off of every single one of these vertexes, right? Like I could draw, I'm going to do it in another color. I could draw this one straight out, and so there's one exterior angle. And I could draw this one straight out, and this is another exterior angle. I could do this one, and that's another one. But all of them, even though there's many, many of them, all of them are very, very small now. Because the inside one is so big. And I'm talking about the inside one being all the way from here to here. We don't care about the triangles when we're talking about this. So interior ones are getting very, very big, so exterior ones are getting very, very small. So it doesn't matter the size, always equals 360 degrees. All the exterior angles added together. Okay. So when a side of a polygon is extended, two angles are created. The angle that is considered to be exterior angle is adjacent to the interior angle at the vertex. So we've got the word adjacent. I don't think we've actually mentioned that before, but you did do that in trig last year. Adjacent means touching. I might want to write that in. Touching. So basically there's an exterior angle and there's an adjacent, a touching interior angle. Those two have a relationship together. So now we just summarize all of our rules. We've got a couple different rules now that we learned in this unit. Convex polygon. Actually, this is a really important definition too. A polygon in which each interior angle measures less than 180 degrees. So that's not a very clear definition, is it, for you guys? What that means is a convex, let's say 5-sided figure. That's a convex 5-sided figure. It means if there was kind of like a middle, all of it is pushed outwards. None of it is bent into the middle. It's all kind of stretched outwards, so all the angles are kind of on the small side. If you think of it like an arm, kind of like bending around, nothing is broken. Nothing is bent backwards. Nothing's, like sticking out like that. Is kind of the idea. So a non-convex one would look like this. This is convex. This is like ballooned out, sticking out. They don't have to be all the same or anything, but they do all have to be sticking out. They all have to be bending the right way. This one is not. This elbow right here is broken. So it's bent the wrong way. The little angle's on the outside. So this guy breaks our formulas. This guy does not work. So the formulas that we're talking about only for convex polygons. So be careful which ones you're using them for. So rule number 1, why don't we number these? Rule number 1, the sum of the measures of the interior angles of a convex polygon with n sides can be expressed as, so this is the formula we derived. That's the most important one of this unit. You're going to use it quite often. There's kind of a small little adjustment to it in formula number 2. We haven't talked about it yet, but it's pretty easy to understand. The measure of each interior angle of a regular polygon. So regular means all sides and all angles are equal. So regular polygon is the perfect shape. If we're talking an 8-sided figure, it's our stop sign. If we're talking a 5-sided figure, this looks pretty close to it. Actually, these are 90 degrees. They'd have to be out a little bit. Our 5-sided figure would look like that. That's kind of our regular 5-sided figure if all these lengths were the same, and therefore all these angles were the same. That would be our 5-sided figure. Our 4-sided and 3-sided, they have names. That's our square. No other 4-sided is regular, only the square. And our equilateral triangle is our 3-sided one. So basically the rule is if it's regular, that means all the angles must be the same. You could find each individual angle. Each individual angle is the sum of all the angles divided by how many angles there are, or how many side lengths there are. There's always an equal amount of angles and side lengths. So take that overall number that we found in that table, or with that formula, and just divide it by how many there were. For instance, with this guy right back here, it was a 12-sided figure. Now be careful, it is 12 that we want to divide it by. Even though it's 10 times 180, it makes 1800. If you want to find out how much each individual angle is, if they're all the same, you would divide that by 12. That's all you gotta do. There are 12 angles, divided by 12. You found how much each angle is. So fairly straightforward. And then we have our third rule, which we talked about. The sum of the measures of the exterior angles of any convex polygon, so as long as it's convex, these ones might be true even if it's not convex. I'm not sure. Usually we're talking about convex though. Actually, I think these are true even if they're not convex. Because if this one gets bigger, these ones just get smaller. So yeah, these are true no matter what. While this one, every regular polygon is convex. So number 2 is convex, but number 1 works all the time. Number 3, the exterior ones of any convex polygon always equals 360. Pretty easy. Okay, another example. Determine the measure of each interior angle, so a single interior angle of a regular 15-sided polygon. Pentadecagon. We could draw a picture of it. That would be rather difficult though. It's a perfectly shaped 15. It's going to have lots of little tiny lines on it. It's going to be hard to do. But anyway, let's find out what the sum of all the angles is. Or we can jump right to this formula. Let's do it in 2 steps though, if we were going to do that. So the sum is equal to 15 minus 2 times 180, which is 13 times 180, which is 2,340. So each angle is equal to 2,340 divided by, there are 15 of them. All you gotta do is divide it by 15. Once you get into larger numbers, these will always be decimals. I imagine this one's gonna be a decimal. Oh, it isn't actually. It's a whole number, 156 degrees. Every single angle is 156 degrees, which is rather large, right? If that's our start of it, 180 degrees would be straight up, so 156 would be something like that. So if you kept going, redoing that angle every single time, you should make a perfect 15-sided shape, is the idea. Okay, hopefully that made sense. Try the practice questions. If you have any questions, ask me. Good luck.